For the first question, we're asked to provide the IUPAC name for the following compounds. For the first compound, we have a cyclohexane ring, and we have an alcohol functional group. We're going to make the parent name cyclohexanol. That alcohol is at the 1 position on the cyclohexane ring, which means my 2 methyl groups are at the 2 position. For the stereocenter, we have, for rankings, what's attached to this carbon, we have the oxygen is ranked first. So the oxygen here is ranked first. The carbon with the 2 methyls is second, and that carbon's third. 4 is in the back, so this is an R stereocenter. So we have R, and then 2, 2, dimethyl cyclohexanol. So cyclohexane, if we just had the ring, but we're taking off the E and adding OL. So it's 2,2 dimethyl cyclohexanol. For this compound right here, the common name for this would be, we have a 1, 2, 3, 4, 5 carbon chain. So pentane, there we have a methyl. So this would be methyl 2-pentyl ether for the common name. For the IUPAC name, we're going to call this a methoxy group. And that is at carbon number 2, and we also have a stereocenter there. So for this, we have a hydrogen coming off that carbon there. So for the rankings, for what's attached, we have 1, 2, 3, 4's in front. This is a clockwise rotation, which would normally be R, but it's S since 4 is in front. So this is 2-methoxy, but I also need to say 2S. So, or we don't need to say 2 because there's only one stereocenter. So S, and then 2-methoxy pentane. For the next question, predict the stereospecific products and propose a mechanism. So here we have a strong nucleophile, and we are not under acidic conditions. We do not have a strong acid. So this is going to do an attack on the less substituted carbon to break open our epoxide and get us to an intermediate. So when our methoxide anion attacks, now we have that carbon-carbon bond here is that carbon-carbon bond here. I'm going to draw my oxygen with my methyl group attached there, which is aligned anti to the oxygen, which now has a negative charge because these electrons went to that oxygen. We still have our 2 methyl groups attached to this carbon. Nothing else is attached there. And now we have a small amount of methanol to protonate our alkoxide anion and get us to our final product, which is Me. And now we have an alcohol functional group there and our 2 methyl groups there. All right, in this case, we have a strong acid in solution represented by our hydrogen cation. So we're going to protonate our epoxide first. That'll get us to our intermediate where we have our oxygen, now with a hydrogen and a positive charge. We've got 2 methyl groups attached. Once we've protonated that epoxide, now this bond right here is weakened. So we have a partial positive charge there, which means we have a partial positive charge on that carbon too. It's pulling most electron density from that carbon because this carbon is a more stable carbocation if it were to be a carbocation. So now our nucleophile, our weak nucleophile, methanol can come in. So we will do a nucleophilic attack on that carbon and break that bond there, which puts our alcohol at the less substituted carbon. We still have our methyl group attached to that, Now we've got our 2-methyl group still attached there, and our nucleophile came in. So we've got our O-methyl group there, and that O-methyl group still has a positive charge and a proton on it. So to get to our final product, we need to deprotonate that using methanol. Strongest base we have in solution. So that methanol can deprotonate that to get us to our final product, which is remarkably similar. We have our alcohol functional group and our methyl group still there, and our 2 methyls there, and now our O-methyl group there. Now notice when we did this backside attack, we still are doing a backside attack even though it has similar properties as an SN1 reaction. It's still a backside attack because we still have that ring. So we are doing a backside attack, which means we push these methyl groups up a little bit. So essentially everything gets pushed up a little bit. We're exaggerating the methyl groups just because it's good to keep drawing our oxygen, carbon, carbon on the same plane. So here are oxygen, carbon, and carbon of the original ring are all on the same plane still. Alright, so that gets to our final product there. For the next question, we need to predict the stereospecific products or starting materials for the following reactions. For this, we've got a strong acid and we have an ether. We have carbons that are pretty substituted right around the ethers, so we're definitely not going to be able to do an SN2 reaction, but we have a strong acid anyway, which basically says we're not going to do an SN2 reaction. So the first step for this is a proton transfer. So these electrons are going to attack that hydrogen, and we're going to have a protonated ether functional group. So now we've got our 2 methyls there still, and our oxygen and isopropyl group. Those 2 methyls didn't look very good. All right, now we have a hydrogen attached here and a positive charge there. So we basically don't have enough room for the backside attack for Br to come in. So it's definitely going to be an SN1 type reaction. Now the question is, do we break this bond here or this bond here? So if we break this bond here, it's going to form the more stable carbocation intermediate. So that's the best choice, which means we're going to have that leaving group leave. So one of our byproducts, I'm going to just write it over here, is isopropanol. So we formed an alcohol functional group. We have 3 carbons in our carbon chain, so 3 carbons, 1, 2, 3, and we have an alcohol functional group. And that alcohol is on the center carbon of propane. This is referred to as isopropanol. All right, the other byproduct that we have is our carbon chain with 2 methyl groups, a positive charge there, and now our nucleophile can come in and do a nucleophilic attack, stabilizing that carbocation like the end of an SN1 reaction, and that gives us our final product, which is now our alkane with a halogen. So these would be the major products. The next one's an interesting one, so there's a lot of options. I think probably the easiest one to put is HOCl, and that means we need to oxidize an alcohol functional group, so that would be a good choice. Another option is if we had an alcohol functional group, we could use a stronger oxidizing agent like H2CrO4. That would also get us to our ketone functional group. And then thinking back to what we looked at earlier, if we have a terminal alkyne, we could also form the same compound. So we need 1, 2, 3, 4 carbons in our chain, and then we can use our water, H2O, and HgSO4, and an acid as well, so H2SO4. So that will actually form an enol, so essentially we're adding water to the more substituted carbon, we're adding our proton to the less substituted carbon, so we'll form an enol, and then that will tautomerize into our ketone. So we'll actually end up with the same compound that ketone functional group. So any of those three answers are fine. If you write them slightly differently, that's fine too. For example, like for bleach, HOCl, usually we have bleach in solution, add acetic acid to it. Once we protonate our OCl, that gets us to HOCl. So this is another good representation for that. All right, in this case, if we have an alcohol and a primary carbon, that's going to fully oxidize this carbon. So instead of forming an aldehyde functional group like it would if we added this, we're going to form a carboxylic acid functional group. So we have our carbon chain here. Now that carbon is fully oxidized. So we've got carbon 1, 2, 3, 4, carbon 1, 2, 3, 4. That alcohol becomes an aldehyde, and then in the next step, as long as we have two equivalents of chromic acid, which is hard to regulate that, because even if we had aldehyde, we'd eventually convert some of that to the carboxylic acid. So this would be the major product. For the next question, we have a weaker oxidizing agent, so this will stop at the aldehyde functional group. So there, instead of having an OH group, we're going to have an aldehyde functional group. To make this compound, there are a lot of different options. Based on what we've looked at in Chapter 9, I think probably the best choice would be to have a carbon chain with a good leaving group on it, like Br, and then add a reagent, not H, so a sulfide with a methyl group on it. So we'll say Me, and then a negative charge on our sulfur. So that way we can do an SN2 reaction, kick that off, and give us this final product here. All right, for this question, we have a strong base, strong nucleophile, and here we have a good methyl donor. So this sulfur wants electrons. It doesn't have any protons to give. So the only way it can get electrons is from this carbon-sulfur bond. So we're going to do a nucleophilic attack on that carbon. These electrons from that carbon-sulfur bond are going to go to the sulfur. So that will give us the two different products. One of them is this, our oxygen now has a methyl group on it, so we converted our alkoxide to an ether. And then we also have our sulfur with two methyl groups on it. Now it is neutral and more stable.